Welcome back to OCR MEI Further Mathematics B, Chapter 2.6, Roots of Unity. So unity means just one. So the roots of unity is essentially the roots or the solutions for a complex number to the power of n, which equals to 1. One thing to note is that because the real solution or the final result is a real number, it always have a conjugate pair solution, and they can occur in multiple conjugate pairs, as I will show you in the examples in a bit. For starters, let's start to find the unity root of z to the 3 equals to 1. So one key aspect of this is to know the exponential form and the modulus argument form. So simply state z or z to be a value of r e to the I theta. So this is both. This can be considered modulus argument or exponential form because they are essentially the same, except that you can save yourself quite a lot of ink. Consider that saving you money or something. That would work. So this is to the power 3 should give you 1. That would be 1. And so from what we know, 1 is essentially a complex number in modulus argument form 1 e to the 0 I, because e to the 0 I is also just 1. 0 denotes the radian on the x-axis, and we know that the real axis x1 is just 1, and so this do fit with a modulus 1 angle 0. So in this case, if we expand this power and apply the Moivre's, or just straight power, then you get r cubed is times e to the I3 theta equals to 1 e to the 0. This is one of the things that you need to be able to tell from just looking at roots of unity. Basically, you want to equate 1 with r to the n e to the I n theta. Now, from this, we can collect like terms or just compare coefficients. So for the modulus, r cubed equals to 1. This is a no-brainer solution, given that modulus has to be real and has to be positive. You get r is 1. There we go. So we're halfway there essentially. Next up, we have the angle. So 3 theta, just literally comparing these two, has to be 0, and thus theta equals 0. Yay, there we go. We have the answer, r e to the 0 I, which conveniently we know is already 1. So that's the solution. But remember, I have taught you before that the power equals to number of roots. We have 1 root so far. Well, what about the other 2? Well, the other 2, we cannot find 2 more modulus from the solution because they do not exist. However, for angles, remember that you have a 2 pi repetition pattern per cycle. And so essentially, for 3 roots, you want to have 3 values for 0, which is 0 in radians, 2 pi, and 4 pi. You can keep going to 6, 8, and so on, but then you go back to 0, 2, and 4. Essentially, it cancels out. The algebra is not stupid, really. So if you divide these two by 3, you get 2 on 3 pi, and you also get 4 on 3 pi. And there you have two other solutions. With that, if you plug it in, then let's see, now I'm not gonna plug it in actually, I'm just gonna leave it in modulus argument form, so you've got 1e to the 2/3 pi and 1e to the 4/3 pi. Now you're gonna tell me, but wait, where is the complex conjugate? Because I've told you complex conjugate have plus or minus complex values, which essentially is the plus or minus angle, same angle. Turns out negative 2/3 pi, if you add 2 pi, you get, I think, 4/3 pi, which means that minus 4/3 pi? No, actually, I'm actually quite stupid, aren't I? Let's see, how do I want to do this? If I take 4/3 2 pi, then take away 4/3 pi, then you will get back to 2/3 pi. Essentially, these two angles are complex conjugates, angles of each other, and it's denoted as shown over here. This is the essential negative 2/3, or if you go all the way around, then you shall get 4/3 pi. And they are the same, they mean the same line, except the argument is negative. So a lot of times you would put the arguments in terms of theta is between plus pi and minus pi, rather than, as I have done before, theta is between 0 and 2 pi. Both of them are the same. You don't have to deliberately say that they are complex conjugates of each other. You could say that Z2 is the first one and Z3 is the second one, and you can write on side notes that Z2 star, or complex conjugate of Z2, is Z3. That would not give you any extra marks, but it is also very true, and it's something that is important for you to be able to recall. And I forgot to mention that this other line will definitely be 2/3 pi. Don't forget that pi. Yeah, basically what you have is also a length 1 spread out angle. So in terms of the angle that we are used to, the degree angle, this is a 120 degree, 120 degree, and a 120 degree. With that said, if we join lines between the 3 dots, or the 3 solution or roots, then we get an equilateral triangle. This is due to the fact that this is a unity root, and the solution always lie within a circle of radius 1. Just from the definition, because all powers that equals to 1 has to start from 1. This applies to any power, and therefore the more ends, the geometry would show a larger number of vertices of a regular polygon. So for z to the cube, it's a triangle. Z to the 4, it's a square. To the 5 is a pentagon. To the 6 is a hexagon. To the 7 is a heptagon. So and so. And they always have complex conjugate pairs. Sometimes -1 is a solution if it's an even number, of which we already know from previous experiences, except we now also know the new complex solutions that are possible. After what seems to be a mouthful of explanation, I'm sure you're now capable of doing some unity questions. But before then, I have to again emphasize that remember the number of roots of an equation has to be equal to the max power of the equation. So this is one very essential rule. It's a fundamental law of polynomials. So it's again really useful, and we will come back to that in the algebra section in chapter I think 6 in the future. Also, modulus argument form and exponential form really useful and crucial in this section. Now it is time for you to do some practice. Find me the roots of z to the 6 equals to 1 and then show them on an argand diagram. I'll give you 5 seconds to get prepared. Pause the video if you need to, and we'll come back with the answer. So in 5, 4, 3, 2, 1. And here we go with the 6 solutions. Note that I have kind of outlined the hexagon. That is, it is a regular hexagon, and these are the 6 roots with z2 and z6 as complex conjugates, z3 and z5 as complex conjugates. z4 is real and -1, z1 is real and +1. That's all for this kind of video. Actually, before I end, do add the argument per root on your argand diagram sketch every time. If they call a label diagram, label the the real and imaginary part axes per root, and for the argument, do label them on your argand diagram. You can use a factor notation on, say, a line for a complex value, but I just denoted them as dots. It's acceptable for you to draw a line from the origin to the point of interest during the exam, and you wouldn't get penalized for it. So don't bother rubbing out your lines. It would work. Anyway, this will be it, and I hope you've learned something. If you have any questions, do let me know in the comment section below, and I will see you on my next one.